Oh, you have a notification. Hello, students. You have a big mission. We are in danger. Thanatos is on his way to destroy Earth. We need to quickly get all the magic stones by exploring how graph and group theory blend to fight Thanatos and save the world.
Hi, I am Firdaus. Nice to meet all of you students. Let's start our journey with the Aurora planet first. Our research began with one key question. How does the Laplacian energy behave in relative coprime graphs of dihedral groups? While past researchers explored certain aspects of dihedral graphs, there was still a gap, particularly for groups with degrees up to 10. So that's exactly where we stepped in to compute, analyze, and understand these new energies. Our mission focuses on three main objectives. First, we aim to construct and determine the Laplacian matrices of the relative coprime graph of dihedral groups for degrees up to 10. Next, we determine the characteristic polynomial of the Laplacian matrices of the relative coprime graph of dihedral groups for the same range of degrees. Finally, we computed the Laplacian energy of the relative coprime graph of dihedral groups for degrees up to 10. Our study focuses solely on dihedral groups with degree up to 10. We used computational tools like Decode Online to build our Laplacian matrices and find their characteristic polynomials, then calculated the Laplacian energy for each graph. Our methodology was carried out in three key phases. In Phase 1, we constructed the Laplacian matrices for the relative coprime graphs of selected dihedral groups, specifically D3 until D10. In Phase 2, we determined the characteristic polynomial of each Laplacian matrix. In Phase 3, we used these results to compute the Laplacian energy.
Wait! Are you ready for the next journey? Good. My name is Adam, and this is the Titanus planet. Hope you are still enjoying collecting the stones. In the implementation stage, we first computed the eigenvalues, denoted by mu, from each Laplacian matrix. These eigenvalues were then substituted into the Laplacian energy formula, summation of the absolute value of mu, sub I minus 2m over n. Using this formula, we calculated the Laplacian energy for each corresponding graph, which reflects its overall structural properties. For example, in the case of D3, our calculations produced a Laplacian energy of approximately 8.67. This section shows the results and discussion of the research. For the odd dihedral groups, namely D3, D5, D7, and D9, we observed several interesting patterns in their Laplacian energies. In particular, the Laplacian energy does not increase steadily with the order of the subgroup. Instead, it follows a non-monotonic trend. For the even dihedral group D6, the Laplacian energy varies depending on its subgroups. Whereas for D4, D8, and D10, the Laplacian energy remains constant across all subgroups. In conclusion, our study successfully achieved all of its objectives. The analysis of the Laplacian energy of relative coprime graphs of dihedral groups with degrees up to 10 revealed distinct patterns and relationships between the group structure and spectral properties, providing new insights into this specific class of graphs. You might be wondering why does this matter? Our research doesn't just stay on paper, it has real-world potential. Graph energy concepts can enhance network analysis, cryptography, and cybersecurity. They could even help design more efficient data encryption and communication algorithms. So while we studied dihedral groups, the impact reaches much further. because graphs are widely used to model real-world systems and connections. Now, I will explain the novelty of this study. First, this research investigates the Laplacian energy of relative coprime graphs derived from dihedral groups. Second, it studies graphs with vertex degrees up to 10, which is a previously unexplored area. Third, it explores the relationship between the algebraic structure of dihedral groups and the spectral properties of graphs. Next, it provides new insights into patterns and bounds of Laplacian energy. Finally, this study fills a research gap in the combined analysis of relative coprime graphs, dihedral groups, and degree constraints. Finally, unlock your box now and claim your power stones. Psst, this is your last stone.
Yay! All stones are unlocked. Oh, you got a new message.
All the magic stones have been collected. You can complete the Infinity Hand.